Hard water contains dissolved calcium, calcium 2+, and magnesium, magnesium 2+, ions that react with soap to form scum. The amount of these hardness ions is usually reported as milligrams of calcium carbonate 3 per liter, milligrams calcium carbonate per liter. This unit works because 1 mole of calcium carbonate 3, 100.09 grams, contains 1 mole of calcium 2+, 40.08 grams, and 1 mole of magnesium carbonate 3, 84.31 grams, contains 1 mole of magnesium 2+, 24.31 grams, so converting to a single calcium carbonate equivalent makes calculations easy. Conversion steps. Step 1. Measure calcium 2+ and magnesium 2+ in moles per liter, for example by atomic absorption. Step 2. Multiply each by its equivalent weight of calcium carbonate, 50.04 grams per equivalent. Hardness equals calcium 2 plus magnesium 2 plus times 50.04 times 1000. Step 3. ppm, parts per million, is numerically the same as milligrams per liter for water because 1 liter is approximately 1 kilogram. So 150 milligrams calcium carbonate per liter equals 150 ppm. Step 4. To obtain molarity of hardness, equivalents per liter, divide milligrams calcium carbonate per liter by 50,040 milligrams per equivalent. Example, a tap water sample shows 200 milligrams calcium carbonate per liter. Hardness, equivalents per liter, equals 200 divided by 50,040, approximately 0.004 equivalents per liter, equals 4 millimoles equivalents per liter. This is a moderate hard water typical of many municipal supplies. In ion exchange, the driving force is the change in Gibbs free energy delta G, when a cation on the resin or zeolite is swapped with a cation in the water. For a simple binary exchange 2R sodium plus calcium 2 plus reversible arrow R sub 2 calcium plus 2 sodium plus, the equilibrium constant K is related to the standard Gibbs energy chain. Delta G naught equals negative RT natural log K, where R equals 8.314 joules per mole Kelvin and T is absolute temperature. A negative delta G naught large K means the exchange is spontaneous, and the resin prefers calcium 2+ over sodium+. Selectivity is quantified by the selectivity coefficient K sub Ka over Na. For a multi-ion system, K Ka over Na equals open bracket calcium 2 plus close bracket times open bracket sodium plus close bracket resin squared, divided by open bracket sodium plus close bracket squared times open bracket calcium 2 plus close bracket resin. A K value greater than 1 indicates the resin has higher affinity for calcium 2+. Temperature dependence follows the Van 't Hoff equation. D natural log K divided by D open bracket 1 over T close bracket equals negative delta H naught over R. Thus, if the exchange is exothermic delta, H naught less than 0 K decreases with rising temperature exactly what is observed for many strong acid-cation exchange resins. Engineers use these thermodynamic relationships to predict how changing water temperature will affect softening performance. Ion exchange kinetics describe how fast the resin sites are occupied as water flows through the column. The simplest model treats the overall rate as pseudo-first order with respect to the concentration of the target ion in the bulk solution. Negative dC over dt equals Kc, where C is the ion concentration, for example calcium 2+, and K is the apparent rate constant per second. Integrating gives C equals C naught e to the negative Kt. In a packed column, the resin particles create a mass transfer zone, MTZ, that moves downstream. The length of the MTZ, L sub MTZ, is related to the residence time, tau, and the kinetic constant. L sub MTZ equals V tau equals V over K. V equals superficial velocity. A small k slow exchange produces a long MTZ and early breakthrough, while a large K fast exchange results in a sharp breakthrough curve. More detailed models, for example the Thomas or Bohart-Adams equations, combine kinetic terms with bed hydraulics, but the pseudo-first-order approach is a useful starting point for design calculations and for interpreting laboratory column tests. Zeolites are crystalline aluminosilicates that act like molecular cages. The basic framework consists of silicon-4 and aluminum-4 tetrahedra linked by shared oxygens. Every aluminum substitution introduces a negative charge that must be balanced by a cation such as sodium, potassium, calcium, and so on. The silicon over aluminum ratio controls two key properties. Ion exchange capacity, abbreviated IEC. Each aluminum atom can host one monovalent cation or half a divalent cation. IEC in milliequivalents per gram is approximately 100% aluminum divided by the atomic mass of aluminum times 1000. For a zeolite with 2 weight percent aluminum, IEC is about 0.4 milliequivalents per gram. Selectivity, higher silicon over aluminum, meaning more silica and less charge, makes the pores more hydrophobic and typically favors larger, less hydrated ions. Conversely, low silicon over aluminum, meaning more aluminum, gives strong electrostatic attraction for small, highly hydrated ions such as calcium. Common framework types used for softening are FAU, also called Y-zeolite, large 12-membered rings, high capacity, good for calcium and magnesium removal. LT, a zeolite 4A, smaller cages, excellent sodium exchange, often used for sodium removal. Exchange isotherms such as the Langmuir model describe how ion uptake, Q, varies with equilibrium concentration, CE. Q equals Qmax times KL times CE divided by 1 plus KL times CE, where Qmax is the maximum capacity and KL is the Langmuir constant, related to selectivity. Experimental isotherms guide the choice of zeolite type for a particular water chemistry. A fixed bed column is designed so that the ion exchange resin or zeolite can treat a given volume of water before breakthrough occurs. The breakthrough curve, C over C naught versus time or volume, is typically S-shaped. T equals N naught Z over C naught V minus 1 over K times Ln of 1 minus C over C naught. T is service time at a particular breakthrough fraction, C over C naught. N naught equals resin capacity, equivalents per liter of bed. Z equals bed depth in meters. C naught equals influent ion concentration. V equals linear velocity in meters per second. K equals kinetic constant per second. Plotting T versus Z for a fixed breakthrough gives a straight line whose slope equals N naught over C naught V. This allows rapid scaling of the column size for larger plants. Residence time distribution, RTD, is measured by a tracer test, for example a pulse of salt. The mean residence time tau equals V divided by Q, where V is bed volume and Q is flow rate. It should be long enough to allow the mass transfer zone to develop fully. Typical tau ranges from 5 to 30 minutes for domestic softeners. Design steps. Step 1. Determine required water volume, V sub W, per regeneration cycle. Step 2. Choose a safe breakthrough fraction, often 0.1 to 0.2 of C naught. Step 3. Use BDST to compute the minimum bed depth, Z. Step 4. Verify that tau equals Z divided by V satisfies kinetic requirements derived from the pseudo first-order model. Regeneration restores the resin's ability to bind hardness ions by flushing it with a concentrated solution of a more strongly preferred ion, usually sodium chloride. A mass balance on the resin for calcium removal gives Q sub Ka exp M resin equals V region C na region alpha na to Ka, where Q sub Ka exp equals amount of calcium ion removed per gram of resin, equivalents per gram. M resin equals total resin mass, grams. V region equals volume of regenerant, liters. C na region equals sodium concentration in regenerant, equivalents per liter. Alpha na to Ka equals stoichiometric coefficient. 2 sodium ions replace 1 calcium ion. Typical practice: use 10% weight per volume sodium chloride solution, which corresponds to approximately 1.5 equivalents per liter sodium. For a resin that has captured 0.2 equivalents per liter calcium, the required regenerant volume per liter of bed is V region equals 0.2 equivalents per liter divided by 1.5 equivalents per liter, approximately 0.13 liters per liter of resin. Chemical consumption calculations must also include the brine waste factor. If the column holds 500 liters of resin, The regeneration step needs approximately 65 liters of 10% sodium chloride and generates roughly the same volume of spent brine that must be disposed of according to local regulations. For zeolite, regeneration is similar but often uses a lower concentration sodium chloride solution because the zeolite's exchange sites are less tightly bound. The same mass balance principles apply, with the zeolite's ion exchange capacity, milliequivalents per gram, replacing the resin's capacity. Fluid flow through a packed ion exchange column experiences a pressure drop delta P that is described well by the Ergun equation. Delta P over L equals 150 times 1 minus epsilon squared mu V divided by d sub P squared epsilon cubed plus 1.75 times 1 minus epsilon rho V squared divided by d sub P epsilon cubed. L equals bed length meters. Epsilon equals bed void fraction, typically 0.35 to 0.45. Mu equals fluid viscosity pascals second. Rho equals fluid density kilograms per cubic meter. V equals superficial velocity meters per second. D sub P equals equivalent particle diameter meters. The first term represents viscous laminar losses. The second term accounts for inertial turbulent losses. In practice, most domestic softeners operate in the laminar to transitional regime Reynolds number less than 2000, so the viscous term dominates. Reynolds number for packed beds is defined as Reynolds equals rho V d sub P divided by mu. Design rule of thumb: keep Reynolds below 500 to avoid channeling and excessive wear on the resin beads. Permeability K of the packed bed can be extracted from the Ergun equation by rearranging the viscous term. K equals d sub P squared epsilon cubed divided by 150 times 1 minus epsilon squared. Higher permeability, larger d sub P, higher epsilon means lower delta P, allowing a smaller pump. However, large beads reduce surface area and may lower exchange rate, so a balance must be struck. Explanation: when choosing between a strong acid cation exchange resin and a natural zeolite for water softening, engineers weigh several factors. Cost: initial. Resin is higher synthetic polymer, approximately $10 to $15 per kilogram. Zeolite is lower mineral, approximately $2 to $4 per kilogram. Capacity: resin 1.2 to 1.8 milliequivalents per gram, high due to many sulfonic sites. Zeolite 0.3 to 0.6 milliequivalents per gram, limited by aluminum content. Selectivity: resin very high for divalent over monovalent, K approximately 10 to 100. Zeolite moderate, depends on silicon over aluminum ratio, K approximately 2 to 5. Regeneration: resin requires 10% sodium chloride, 0.13 liters per liter of resin, higher brine cost. Zeolite often regenerates with 5 to 7% sodium chloride, lower brine volume. Service life: resin 3 to 5 years, depends on fouling and pH. Zeolite 1 to 2 years, more susceptible to silicate fouling. Pressure drop: resin slightly higher, smaller bead size. Zeolite lower, larger and more uniform crystals. Temperature sensitivity: resin exchange efficiency drops with temperature increase. Exothermic: zeolite less temperature dependent, more stable structure. Overall, resin is preferred for high hardness, high throughput municipal plants where capacity and selectivity outweigh the higher capital cost. Zeolite becomes attractive for small-scale or rural installations where low initial cost and simple regeneration are more important. Annual cost equals capital expenditure divided by service life, plus regenerant cost times cycles times regeneration volume plus energy cost times delta pressure times flow rate. Plugging typical numbers shows resin-based units often have lower total cost after 3-year amortization, despite the higher brine usage. 1. Hardness calculation. A water sample contains 80 milligrams per liter calcium 2+ and 30 milligrams per liter magnesium 2+. Compute hardness in milligrams per liter calcium carbonate. Convert to equivalents. 80 milligrams calcium 2+ times 1 equivalent per 40.08 grams equals 0.002 equivalents per liter. 30 milligrams magnesium 2+ times 1 equivalent per 24.31 grams equals 0.0012 equivalents per liter. Total hardness equals 0.0032 equivalents per liter. Hardness equals 0.0032 equivalents per liter times 50,040 milligrams per equivalent, approximately 160 milligrams per liter calcium carbonate. 2. Selectivity coefficient. In a column, equilibrium concentrations are calcium 2 plus equals 2 milligrams per liter, sodium plus equals 100 milligrams per liter. Resin phase concentrations expressed as equivalents per gram of dry resin are calcium 2 plus sub raise equals 0.02 equivalents per gram, sodium plus sub raise equals 0.06 equivalents per gram. Compute K sub Ka over Na. Convert water concentrations to equivalents. 2 milligrams calcium 2 plus divided by 40.08 equals 0.00005 equivalents per liter. 100 milligrams sodium plus divided by 22.99 equals 0.00435 equivalents per liter. K equals 0.00005 times 0.06 squared divided by 0.00435 squared times 0.02, approximately 0.53. Since K is less than 1, the resin prefers sodium plus over calcium 2 plus under these conditions. 3. BDST design. Desired service time equals 30 days at 100 liters per hour. Inlet hardness equals 250 milligrams per liter calcium carbonate. Breakthrough fraction equals 0.1. Resin capacity N0 equals 1.2 milliequivalents per liter of bed. Kinetic constant K equals 0.02 per minute. Convert flow Q equals 100 liters per hour equals 1.67 liters per minute. Convert hardness to equivalents per liter. 250 divided by 50,040 equals 0.005 equivalents per liter C0. Service time T equals 30 days equals 43,200 minutes. Using BDST simplified linear form, T equals N0 times Z divided by C0 times V, where V equals Q divided by area. Assume column diameter 0.2 meters. Area equals pi times 0.1 squared equals 0.0314 square meters. V equals 1.67 liters per minute divided by 31.4 liters per cubic meter equals 0.053 meters per minute. Solve for Z. Z equals T times C0 times V divided by N0 equals 43,200 times 0.005 times 0.053 divided by 1.2, approximately 9.6 meters. Hence, a approximately 10-meter deep bed or multiple stacked columns would meet the requirement. 4. Regeneration volume. A 500-liter resin bed has captured 0.2 equivalents per liter calcium 2 plus. Using 10% sodium chloride, 1.5 equivalents per liter sodium plus, determine regenerant volume. Required sodium plus moles equals 2 times 0.2 equivalents per liter times 500 liters equals 200 equivalents. V subregion equals 200 equivalents divided by 1.5 equivalents per liter, approximately 133 liters. Approximately 130 liters of brine will restore the resin. Short answer concepts. Why is hardness expressed as calcium carbonate? It provides a single scale that represents the combined effect of calcium 2 plus and magnesium 2 plus using a common equivalent weight. What is a mass transfer zone? The region in the column where ion exchange is actively occurring. It moves downstream as the resin becomes exhausted. How does silicon over aluminum ratio affect zeolite selectivity? Lower silicon over aluminum, more aluminum, increases negative framework charge, strengthening electrostatic attraction for divalent cations. Higher silicon over aluminum makes the zeolite more hydrophobic and less selective. What happens to delta P if flow rate is doubled? In the ergon equation, the viscous term varies linearly with V, while the inertial term varies with V squared. Therefore, delta P roughly increases between 2 and 4-fold depending on the Reynolds regime. When would you choose zeolite over resin? When capital cost must be minimized, water hardness is moderate, and regeneration chemicals are scarce or expensive.